Hello and welcome to this new video where we are going to discuss basically a very famous paper that was published in the Science magazine in 1972. And the title of this article was or is More is Different. And as a subtitle, Broken Symmetry and the Nature of the Hierarchical Structure of Science by Anderson. Now, the main point of the article is, I'm just going to read through a few paragraphs here so that you get a feel of what are the examples being put forward. And of course, this is open access, so you will get access to it I will put the link in the description. So let's have a quick look here. So the reductionist hypothesis may still be a topic for controversy among philosophers, but among the great majority of active scientists, I think it is accepted without question. And as you know, on this channel, what I like to do is get rid of this without question, and therefore I question, and basically that's it. Now the questions people may say are completely stupid, are silly, they simply demonstrate my inability to understand technical things, etc. I personally don't care. I'm genuinely inquiring, and as long as I don't understand or I'm not convinced, I simply continue to question. And I think that that's what science should be about, um, or at least true skepticism, if anything. So, um, so it is accepted. So the workings of our minds and bodies and of all the animate or inanimate matter of which we have any detailed knowledge are assumed to be controlled by the same set of fundamental laws, which, except under certain extreme conditions, we feel we know pretty well. And again, that's quite telling. If you listen to people like Sean Carroll, for example, has had multiple lectures that he gave or presentations that he gave, in where he stated that he was sure that even in 5,000 years, well, basically the description of matter on Earth or physics on Earth would be the same as it is today. I don't know. I can't tell. I don't have that level of confidence. Um, as he says here, it seems inevitable to go on uncritically to what appears at first sight to be an obvious corollary, of reductionism. And this corollary is the following. If everything obeys the fundamental laws, then the only scientists who are studying anything really fundamental are those who are working on these laws. And what is fascinating is that this particular statement echoes at least a knowledge statement by Rutherford, who in the beginning of the 20th century would have said, purportedly, that all of science is basically is physics, the rest is stamp collecting. And there is a feel when people study physics that basically they are studying the queen of sciences, and all the rest is kind of application of physics. So at least that's the experience I have had. That's the experience that colleagues have reported, and that's clearly the experience I see in the way many physicists behave online or in public. Um, so so here he actually quotes a very well-known passage from Weishaupt, who was one of the leading experts for the Manhattan Project, and also Nobel Prize winner. So looking at the development of science in the 20th century, one can distinguish two trends which I will call intensive and extensive research, lacking a better terminology. In short, intensive research goes for the fundamental laws, extensive research goes for the explanation of phenomena in terms of known fundamental laws. Now, by the way, this is maybe what Kuhn would have said, paradigm change and normal science. At least that's maybe my interpretation of it. As always, so that's where am I. Distinctions of this kind are not unambiguous, but they are clear in most cases. Solid-state physics, plasma physics, and perhaps also biology are extensive. high energy physics and a good part of nuclear physics are intensive. Now we need to keep in mind that Weishaupt was a high energy particle physicist and nuclear physicist. So I think I think it's kind of strange to view it this way, really. Um, and there is always much less intensive research going on than extensive. So again, that's kind of the view that was put forward by Weishaupt. Um, so, and just to continue here, the effective. So that's now Anderson saying the effectiveness of this message may be indicated by the fact that I heard it quoted recently by a leader in the field of material science, who urged the participants at a meeting dedicated to fundamental problems in condensed matter physics to accept that there were few or no such problems and that nothing was left but extensive science. Okay, so here this is a philosophical discussion about the philosophy of science and some sort of taxonomy and hierarchy in terms of which science is more fundamental and which topics within this particular science is more fundamental. And I think that's the main point that here Anderson is trying to address and argue against. So as he says, the main fallacy in this kind of thinking is that the reductionist hypothesis does not by any means imply a constructionist one. So what it means is that the ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe. Um, and so, and here he goes on basically mentioning something. So I'm just going to jump some parts. Of course, you can feel free to read it, but to start with a kind of very nice example he looks at. The main crux of this particular paper, because then we are going to see some other papers of this kind a bit later, is that there is symmetry, right? So many people have learned that modern physics is relying on symmetries in the system, and essentially what you're going to observe are going to be betraying these fundamental symmetries of the fundamental laws. And the example that he gives here is with the ammonia molecule. So if you take the ammonia molecule, we know that the chemical description of it is a pyramidal structure where you've got three hydrogen as a basis, and then the apex at the top is like the nitrogen, and that's kind of the pyramidal shape of the ammonia molecule that is given everywhere. Now, if you have this particular shape, then in principle, as depicted here by this minus plus mu, you would expect that there is a permanent dipole for this molecule in its, let's say, ground state, so-called. And as it turns out, the Hamiltonian of that system is actually symmetric under the orientation of that pyramid. So if you actually have the N, so the nitrogen that is up, or if you invert the pyramid and the nitrogen now is pointing down, essentially the Hamiltonian is um, oblivious to that change. Okay, so that's a symmetry. That's called the parity symmetry, or at least that's a mirror symmetry with regards to the plane where the hydrogen atoms are living. Okay, and as it turns out, when you then find stationary solution of this equation, you need to find solution by this particular symmetry. And because the pyramidal structure is actually violating that symmetry, then the actual eigenstate or acceptable quantum mechanical solution of the Schrödinger equation is going to be here a linear combination of the up, kind of the nitrogen pointing up pyramid and the nitrogen pointing down pyramid. And the way it works is that there is a sort of barrier in between. And the way it works is that the nitrogen actually tunnels, like quantum tunnels through the barrier and then basically moves very fast between these two locations, so these two locations of the apex of the pyramid. And so overall, the quantum mechanical dipole moment in that particular state, which is the allowed one, is zero. And there is no indeed dipole moment, and therefore it's not violating this idea that the symmetries of the fundamental laws are somehow giving effects into the molecule here. And what he says is that, in fact, this nitrogen moving from one side to the other of this kind of pyramidal structure happens 3 times 10 to the 10 times per second. Okay, so that's quite a lot. Now, what he tries to get on is, okay, let's try to imagine, instead of an ammonia molecule, let's try to imagine some more complicated molecules. And so he actually mentions some of them, etc. And then he goes on to talk about sugars. So where is it? So yeah, exactly. So he says that biologically, for example, where is it? Yeah, so sorry. So if you take like molecules that are such as sugar, that have about 40 atoms, if you consider them, so they also have this parity symmetry I mentioned. But if you consider them in biology, you're always going to find them only so-called left-handed or right-handed, only one way. So that's what he says here. Um, um, blah, blah, blah. At this point, we must forget about the possibility. So every sugar molecule made by a living organism is spiral. So it has some chirality, so-called, in the same sense, and they never invert, either by quantum mechanical tunneling or even under thermal agitation. Okay, so what that means here is that the same, if you take one molecule, this molecule is not going to play invertible stuff. Like, it's a very complex structure that doesn't have the ability to kind of invert itself. So if you will, in terms of the barrier I mentioned earlier, the barrier is too high basically to basically tunnel through. Um, so that's basically for large molecules. But then the symmetry is actually satisfied in a different fashion. And that's what he actually mentions here. If, on the other hand, we synthesize our sugar molecules by a chemical reaction, more or less in thermal equilibrium, then we are going to get in the same proportions molecules that are, let's say, left-handed and molecules that are right-handed. Okay, so basically the symmetry is going to be satisfied at the population level rather than looking at a single molecule um, over time, for example. Okay, so here what he says is that we've got a broken symmetry. So the the actual symmetry of the underlying Hamiltonian or Lagrangian, etc., are not upheld by a single big molecule or assembly, realization, if you will, assembly of these atoms. Um, Now, they also mention, so basically it goes on with various examples like this. So, of course, I don't want to be too long here. Um, Things related to the nucleus as well. So even in nuclear physics, these things do actually matter. Um, and then they also show, for example, that more often than not, if you combine multiple particles, actually the resulting symmetry of the whole is lower than the symmetry of the underlying kind of laws. And the example given here is crystals. If you take the Lagrangian again or Hamiltonian, and you look at the symmetries of these guys, then usually there is symmetry like by rotation and stuff like that, and by translation and all that. But then as soon as you um, obtain a crystal through phase transition, then you're going to obtain a phase of matter that has a much lower symmetry. So, for example, the rotational symmetry is discrete if you consider like crystals with Bravais lattices, um, and basically that's it. So, so basically, the symmetries of the whole do not necessarily represent and are much smaller than the symmetries of the others. And there is this idea as well that more often than not, we observe something experimentally, and then it takes kind of forever to understand these things, like from a theoretical standpoint, because they are completely new, unguessable emerging properties. Now, in fact, here, just to come back to this quote here by Weiskopf, one of the quotes I'm aware from the same author, so from Weiskopf, is actually um, he stated, and I will try to put the quote somewhere on the screen. He basically stated that if we had from these fundamental laws of physics, if we had to guess the phases of matter, then we would probably have guessed the crystalline phase, okay, corresponding to some sort of ground state, etc., and the gas phase. But probably we would have never been able to figure out the liquid phase, because this liquid phase is very strange. It's disordered, so you keep the symmetry of the gas, but somehow you are just denser. And so that's something that probably you can't necessarily predict, just like from the get-go. Um, you need to do really something else. So I will try to find this quote there. Um, and so that's the main point I think he's trying to take. So again, you can continue looking at further examples given. Um, and here, I'm just going to. So here, like this passage was interesting. In some sense, structure, functional structure in a teleological sense. So teleological, just in case you don't remember what that means, it has to do with a sort of sense of purpose. So something happens for a reason and not because of something. Okay, as opposed to mere crystalline shape, must also be considered a stage, possibly intermediate between crystallinity and information streams in the hierarchy of broken symmetries. Um, so I think that that's kind of the point, is that there are things related to macroscopic stuff that are really that look like almost kind of teleological. And just to finish here with this quote, um, so he says, well, in closing, I offer two examples from economics of what I hope to have said. Marx said that quantitative differences become qualitative ones, but a dialogue in Paris in 1920s sums it up even more clearly. Fitzgerald says the rich are different from us. Hemingway says, yes, they have more money. So qualitative differences here. And I'm just going to finish by actually an anecdote. When I was doing my PhD, I was working on some kind of statistical mechanics project related to biology, and some of my colleagues were also looking into statistical mechanics of biology and etc. And at some point, they went to a specific event, and this event had plenty of other PhD students, and some of them were working on particle physics and so on. And in fact, my colleague was working on some statistical mechanics of the cell, and in particular inside the cells, and this had to do with um, especially like uh, muscle cells. There is so-called like actin and myosin and all these things. And so he was looking at the statistical mechanics of this stuff. And at some point, like one PhD student was doing his thesis, their thesis. I don't know actually if it was a man or a girl, but what he said was, he said, "Oh yeah, I'm working on cells and stuff in biology," and then the person replied, "Oh, but cells, are they fermions or bosons?" And I don't know if any of you have any idea about this, but that's a very strange question, right? To ask about the cell. It's as if somebody was asking to me if I'm am I a boson or a fermion? I don't know. It could be there is an answer to that. Um, but I think it sums it up. Like some properties emerge at least that's the point being made here. Some properties emerge, some of them disappear, and so it's very difficult to actually reconstruct them ab nihilo, if you will, without any experimental observation backing them up. Okay, so basically that's it. If you've got any questions, comments, or anything like this, please let me know in the description. And again, I'm going to talk a bit more about this idea of more is different in upcoming videos.